Hi everyone. If you're studying AQA Combined Science, sometimes called Trilogy, or AQA GCSE Chemistry, and you just want one video that you can sit down and watch to revise the whole electrolysis topic, then keep watching till the end of this video. First of all, what is electrolysis? Well, electrolysis is where we use electricity to split apart a compound. So I've got here some zinc chloride, that's zinc joined to chlorine, and with electrolysis I should be able to split it apart to produce some zinc and some chlorine. So this is the zinc chloride I'm going to try and split apart, and going into the zinc chloride I've got two carbon electrodes. One's connected to the positive side of the power pack, that's called the anode, and the other carbon electrode is connected to the negative side of the power pack, and that's called the cathode. Remember, panic, positive anode, negative is cathode. But you can see at the moment, even though the power pack switched on, you can tell from the bulb there's no electricity flowing through the circuit or through the zinc chloride. And that's because at the moment we've got the zinc chloride as a solid. And you'll remember from topic 3 that ionic substances do not conduct electricity when they are solid. And that's because the ions are held in place by strong electrostatic forces, and they're held in place in a giant lattice. If you need a reminder about ionic substances and ionic lattices, I'll put a reminder up here now of a previous video. The electrolysis will only work when the ions are free to move. So we could either dissolve the substance in water, or in this case we're melting the zinc chloride so that the ions are then free to move and the zinc chloride will conduct electricity. We can see from the light bulb that the zinc chloride is now starting to conduct electricity now that it's molten. I'm going to use some blue litmus paper, which I'm making damp by dipping it in water, and I'm going to hold it next to the positive anode. And at the positive anode, we should see some chlorine gas being made, and that will start to bleach the blue litmus paper. And there we can see at the end of the litmus paper, it's losing its colour, which shows us that chlorine gas has been made. You can also see some zinc forming at the negative cathode, and now we're going to have a look at how we've managed to split apart the zinc and the chlorine. So here's the electrolysis cell. We've got two electrodes connected to a power supply, and the liquid, once it's melted into a liquid, we call that the electrolyte, and that's just a liquid containing ions. So one side becomes positive and one electrode becomes negative. So how do we remember which is the anode and which is the cathode? Well, we remember panic, and that stands for positive anode and negative is cathode. So we can now label the negative cathode on the right, and in this case the positive anode is on the left. We also need to consider what ions zinc chloride is made up of. So zinc is in that central part of the periodic table, the transition metals, and if in doubt they make 2+ ions. And chloride, well, chlorine is in group 7, that's a halogen, they all make 1- ions. Now during electrolysis we need to remember opposite charges attract. So that means the zinc ions will move towards the negative cathode. So zinc is made at the cathode, as we saw in the practical. The chloride ions, because they're negative, they will be attracted towards the positive anode. So chlorine is made at the anode, which is what we saw, and it bleached the blue litmus paper. That proved it was chlorine gas. So this is a classic case of electrolysis. Remember, electrolysis is splitting up a compound using electricity. So we can see we've got zinc being made at the cathode and chlorine being made at the anode. So we've managed to split apart the zinc and the chlorine in zinc chloride. This next section is just for higher tier students only, and that's how to write half equations for what's happening at each electrode. Now the golden rule is during electrolysis ions change into atoms. So let's think about the example we've just considered, which is zinc chloride. At the cathode we saw zinc ions changing into zinc atoms. So we've got zinc ions on the left, zinc atoms on the right.
Now, because it's a 2 plus, we know that 2 electrons are going to be involved somewhere. So do we put those 2 electrons on the left or do we put them on the right? Well, the answer is we put them on the left because the charge on each side of the equation has to balance. So on the left, we've got 2 plus and 2 minus. That equals 0 charge, and we've got 0 charge on the right. So we've put it on the correct side. And there are rules you can follow. So for example, at the cathode, they're always going to be gaining electrons like this. At the anode, we've got chloride ions changing into chlorine atoms. So here's the chloride ions changing into chlorine atoms. And that means we've only got one electron to consider because it's 1 minus charge. So does the electron go on the left or the right? Well, in this case, we're going to put the electron on the right so that the charge in the equation balances. That means that we've got 1 minus charge on the left and we've also got 1 minus charge on the right. If we tried to put it on the left, we'd have 2 minus on the left and no charge on the right. So it must go on the right in this case. And once again, at the anode, the electron will always go on the right hand side of the equation. But we've not quite finished with this one. We have to remember that chlorine is a halogen, and halogens form what's called diatomic molecules. This means they go round in pairs. So instead of them just going round as Cl, they pair up as Cl2. So to get to that position, we simply double up in the second stage of this equation.
One of the uses of electrolysis is to extract metals from their ores if they're above carbon in the reactivity series. For example, aluminium comes from an ore called bauxite, which is aluminium oxide. And we use aluminium for lots of things, including kitchen foil and drinks cans. Now, we can't simply heat up aluminium oxide with carbon to take away the oxygen like we would if we were dealing with iron ore. And that's because aluminium is more reactive than carbon. So carbon can't reduce aluminium, it can't take the oxygen away from it. So in this case, we have to use electrolysis. Let's have a look now how that would work.
So the way we do get aluminium from its ore is by electrolysis. Remember, the word ore means the rock containing the metal compound. So in this case, the ore is bauxite and it contains aluminium oxide. Now the electrolysis cell looks a little bit different to previous ones we've seen. We've got several anodes connected to the positive of the power supply. And if you're wondering where the cathode is, it's the container itself. By lining it with carbon, it conducts electricity, and then that's connected to the negative side of the power supply. Now, if you can't remember why carbon in the form of graphite can conduct electricity, I'll put a link up here to a previous video which explains that. Now, remember, in electrolysis, the substance needs to be melted. Now, in this case, the electrolyte is molten bauxite, which is aluminium oxide. So we've actually melted the rock, which would take an incredibly high temperature. So to lower that melting point, it's mixed with a substance called cryolite to lower the melting point of the aluminium oxide. And once it's been melted, those ions are then free to move, so it can carry out electrolysis and conduct electricity. So because it's aluminium oxide, in that electrolyte there will be aluminium ions, which are Al3+, because aluminium's in group 3, and there'd also be oxide ions, which are O2-, because oxygen is in group 6. Let's first of all consider what's going on at the anodes. So the anodes, remember, are positive. Remember, panic, positive anode, negative is cathode. And we've got these ions in the electrolyte and they're free to move about because we've melted it. So the oxide ions move towards the positive anodes because the oxide ions themselves are negative. And remember, opposite charges attract. When they get to those anodes, they will lose 2 of their electrons and turn into oxygen atoms. Remember, during electrolysis, we've got ions changing into atoms. So the oxide ions turn into oxygen molecules eventually, and the oxygen is made at the anode. So if we do that in two stages in terms of the equation, we've got the oxide ion turning into an oxygen atom, but then we've got to remember that oxygen forms pairs of atoms. It goes round as O2 molecules, so we need to double that up, and that's what we get for the actual final half equation for the anode. Very often on your exam you could be asked what happens to the carbon anodes over time. Well, the carbon of the anode itself reacts with the oxygen that's being formed there to turn into carbon dioxide. So essentially the carbon anode is changing into a gas, so it's withering away, and we would see carbon dioxide given off at the anode rather than the oxygen that's originally formed. So that does mean the anodes need replacing quite regularly. Let's now consider what's going on at the cathode. Remember, the cathode is the carbon lining which is connected to the negative side of the power supply. Remember, from panic, negative is the cathode. So all of the container essentially becomes negatively charged. That means it's going to attract the oppositely charged aluminium ions, which are positive ions. So they get attracted towards the carbon lining. And here we will see aluminium forming, and it will be molten aluminium because it's all carried out at a high temperature so that the ions are free to move. So if we think about the equation for aluminium ions turning into aluminium atoms, in this case the 3 electrons must go on the left, so that the 3 positive of the aluminium ions and the 3 negative electrons are no charge on the left and no charge on the right. You can also get asked on your exam, why is aluminium so expensive? And the two main reasons for that are that it requires large amounts of electricity to do the electrolysis, and also it requires large amounts of energy in order to melt the bauxite.
Remember, for electrolysis to work, the ionic substance needs to be in a liquid form so that the ions are free to move. So all the examples we've looked at so far have been where we've simply melted the ionic substance and turned it into a liquid that way. The other thing we can do, of course, is to dissolve it in water and turn it into a solution. That way the ions are also free to move, and that's what we've got here. I'm carrying out electrolysis on some copper sulfate solution. So I've got the copper sulfate solution, I've got 2 carbon electrodes and a power supply. The electrode connected to the positive side is the anode, and this electrode connected to the negative side is the cathode. So we'll come back to that in 5 minutes to see what's been going on. If we look closely at the anode, we can see that there's a gas being made. And if we look at the negative cathode, we can see there that we've got copper forming on the cathode. We're now going to see what ions might be involved and what that gas could be that we saw being made at the anode. Whenever we carry out electrolysis of a solution, we've got to remember that the substance is in water, and those water molecules, when we put electricity through them, break apart or dissociate to make hydrogen ions, H+, and hydroxide ions, OH-. So if we try and work out what's going on in the electrolysis of copper sulfate solution, the one we've just seen in the practical, the solution is going to be made of copper ions, Cu2+, sulfate ions, SO42-, but we also need to remember the hydrogen ions, H+, and the hydroxide, OH- from the breakdown of the water molecules. And when the electric current passes, the positive ions will move towards the negative cathode, and the negative ions will move towards the positive anode. So we can see here the ions that move to each side because opposite charges attract. So the negative cathode attracts all the positive ions, and the positive anode attracts all of the negative ions. So what happens at the cathode? Will it be copper that's made or discharged, or will it be hydrogen that's made or discharged? Well, we need to remember the rule that at the cathode it's the least reactive one that is discharged. So in this case, copper is made because copper is less reactive than hydrogen. To work out what happens at the anode, we need to remember the rule that if a halide ion is present, that's any group 7 ions like bromide, iodide, chloride, etc., then the halogen will be made. If not, oxygen is made from the hydroxide ion. And we can see in this case there is no halide ion, so oxygen is made. If you're studying for the higher tier paper, you'll need to be able to write the half equations for electrolysis. So if we start with the cathode, first of all we've got ions changing into atoms, as we always do in electrolysis, and in this case we've got copper ions changing into copper atoms. So we need to put 2 electrons somewhere. If we put them on the left, we can see the total charge on the left is 0 because 2 plus and 2 minus cancel out. And we can see at a glance there's no charge on the right. At the anode, when we get oxygen made from the hydroxide ions, I'm afraid you'll just have to remember this equation. So we start with 4 hydroxide ions. It makes 1 molecule of oxygen, 2 molecules of water, and 4 electrons are left over. So looking at the electrolysis of solutions leads us on nicely to the required practical. So to set up the required practical, I've got an electrolysis cell which has got the sodium chloride solution in, and it's connected to a power pack. I'm making sure that the power pack's only on 4 volts, so it's a safe amount of electricity to put through a solution. Please don't try this at home because, as you know, it can be very dangerous putting electricity through a solution. And the positive side is connected to this carbon electrode, so that will be the anode, whereas this carbon electrode is connected to the negative side, so that will become the cathode. So that we can collect any gases that are given off by the electrodes, I've also got a test tube here filled with the same sodium chloride solution, and I'm going to invert it, turn it upside down on top of the electrode. So that all the solution doesn't fall out, I've managed to cover it, the top of it, with some cling film. So we'll turn that upside down, push it over the electrode, and we'll do the same with the other electrode. This tube is also filled with the same sodium chloride solution. And then the next thing for me to do is remove that cling film. In this required practical, you're expected to predict what would be made at the anode and cathode. So in the case of sodium chloride solution, the ions that would be present would be sodium ions and chloride ions from the sodium chloride, and we'd also have hydrogen ions and hydroxide ions from the breakdown of the water molecules. And when we turn the electricity on, opposite charges will attract, so that Na plus and the H plus will move over to the cathode, and the Cl minus and the OH minus will move over towards the anode. So here we can see how the positive ions have gathered towards the negative cathode and the negative ions have gathered towards the positive anode. When we try and work out what happens at the cathode, we can see we've got sodium ions and hydrogen ions, and we need to remember the rule is the least reactive one is discharged or made. So that means in this case hydrogen is made because hydrogen is less reactive than sodium. When we try and predict what happens at the anode, we've got chloride ions and hydroxide ions being attracted to the anode, and the rule is if we've got a halide ion, the halogen will be made. So in this case chlorine is made because Cl minus is a halide ion. Now let's get back to the required practical and see if our predictions are true. I've now turned on the electricity and we can see that bubbles are forming, so we know electrolysis is happening, and we've got gases of some description being made at each electrode, and we can see there they're starting to fill up the test tubes at each side. We're now going to test the gases that have been made in these test tubes above each electrode. For all 4 gas tests that you need to know, I'll put a link up to a video now. So starting with the negative cathode, we predicted that hydrogen gas would be made at this electrode. So the test for hydrogen gas is to use a lit splint and you should get a squeaky pop. So let's see if it is hydrogen gas that we've made. There we go. We predicted that the gas that would be made at the positive anode would be chlorine gas, and the way we test for this is to get some blue litmus paper, dip it in water to make it damp, and then we hold it next to the open mouth of the test tube, and if it's chlorine gas it should bleach the litmus paper and start taking some of the colour out of the paper. So we can see there it is starting to take the colour out of the blue litmus paper. So that proves we have made chlorine gas. So let me know in the comment section what you think of this whole topic video. I've also got some exam question walkthroughs that go along with this video. I'll put a link up here to those now. And don't forget to subscribe so you don't miss out on future videos. Thank you for watching.